Hey guys, what is going on? Welcome back to another video here on the channel. In this week's video, we're going to be taking a look at the relationship of kV versus power. Now obviously kV is a very important parameter as it relates to the radio control hobby. Once you get into the hobby and you start to play with power systems, you are going to come across the requirement and need to understand this value. And then when we're talking about power is obviously something that's also very important to us. If we don't have any power, there's not going to be much fun with our radio control vehicle. And if you think anything like me, the more power that we can have, the better off that we are going to be. You can see that talking about power on this channel is quite important. Let's head over to the whiteboard and understand the relationship of kV versus power. Before we jump right into the content here on the whiteboard, I do have to warn you that a lot of the stuff we're going to talk about is very wordy in terms of the numbers and values we're going to talk about, as well as the theories that we're going to talk about. However, I do promise that I'm going to keep things as simple as possible. Let's get started and talk about the definitions here in the top left corner of our whiteboard. Here we define power in two different ways. We first define it in an electrical format, and we also define it in the mechanical format. Electrical power is simply the voltage and the current multiplied together, and what you get is a value in terms of wattage. Now, if you do the exact same thing for our power is essentially equivalent to RPM multiplied by torque. Now, if you truly take RPM and you multiply it by torque, let's say in foot-pounds, you're going to have to add a coefficient there. It's something like 52, where you divide it by that value, and you're going to get power in horsepower. Now, if you take RPM in rads per second, as well as torque in Newton meters, you're going to get wattage as your mechanical output power, which is essentially the same wattage that we're talking about when we're referring to the electrical power. So now let's get into definitions of kV. kV is essentially a constant. This is what the big K stands for, and the small v refers to velocity. This is not kilovolts. It has nothing to do with kilovolts. So just keep that in mind, and this is equal to RPM that you get out of that motor for every volt of voltage that you apply to it. Now this is a simplification of RPM just for the sake of getting through this video. Now if we look at another value, and that is kV is equal to 1 divided by kT, we introduce this kT value, which is very important to us because kT, the T here in the kT value, refers to torque, and torque obviously is something we are interested in because we like RPM plus torque in order to get that power that we are after. So now if we take everything that we've learned and we throw it back into this equation of power as it relates to the mechanical world, we plug in power is equal to, and we know that RPM, when we're looking at our brushless systems, we take the kV value, let's say it's 2200, we multiply it by the voltage we plan to run, maybe it's 22.2, and then we know approximately what kind of RPM we expect to get unloaded from that motor system. So we simply just plug that formula in here, kV multiplied by volt, multiplied by the same thing. When we look at torque, we just learned what torque is. Now we take torque and it's equivalent to kT multiplied by current, exactly the same as what we do here for our kV multiplied by volts. Then when we go back to what we learned here, kV is essentially 1 over kT. So we can take kV, we could take kT, put 1 over kV, because that is what kT is equal to. Now we ended up with something here that represents essentially volts multiplied by amps. And the reason we can do this is because you take something kV, you divide it by itself, and you get 1. And that's why we're ending up with this. So this isn't looking so good for does kV actually represent power, because essentially we're just left with power is equal to volts times current again, and we've been able to eliminate the kV value right completely from our equation. So now let's go down here and take a look at an example. We're going to use the same size motor. Every time we're trying to make a comparison, that this applies to the whole entire video here. We are talking about motors that physically are the same size, and there is no difference there. It's not fair to compare a very small motor that has a really high kV versus a really large motor that probably is going to have a much lower kV. Our examples here is a 2500 kV motor versus a 5000 kV motor. We have 24 volts as the max for our 2500K motor, and we have 50 amps, the maximum amount of current that we can pull from that motor as well. And our 5000 kV motor is going to have 12 volts as a max, as well as 100 amps as the current max for that motor. When we look at typical motor specifications, they often give us a maximum RPM. In this case, it's going to be 60,000 RPM, which is quite typical for this type of motor. Then we look at the max wattage, and that's about 1200 watts for our area here. This 1200 watts essentially reflects the multiplication of these values. 24 multiplied by 50 is that 1200 value, and 12 volts multiplied by that 100 value there is going to be our 1200 watt scenario. So now what we know is a bunch of specifications of our motor. However, we're ultimately interested in, does power equal RPM times torque? We know that RPM is going to be the same because it tells us the maximum is 60,000 RPM, but it doesn't tell us any torque values. All this tells us is maximum current values. But because we know this relationship we just learned, KT is equal to the torque per amp of our system, we can then use that equation, and we're going to do this by converting our kV to a KT value, which is taking 1 over kV, 1 over 2500. We multiply that by 50, and we get this value of 0.02. Now, this value doesn't actually have any usefulness to us because the units have not been properly converted. When you properly convert the units, as the number I have there below, for radians per second, we get a value of 0.19 Newton meters. 0.19 Newton meters is a direct torque value that we can use and compare. We look at our next value here, the 5000 kV motor. We multiply that by 100, and we get this 0.02 unitless value here, as well as the same 0.19 Newton meters. Essentially what we have learned is both of these motors are going to produce the exact same amount of torque. And what we can conclude from this is that there essentially is no power difference for these motors. The maximum amount of RPM is the same for both motors, and the maximum amount of torque that we can pull from these motors is also identical, meaning that the power measured in wattage, horsepower, or whatever else that you like to measure power in is going to be identical. There is no advantage for the specific kV that we have seen in this exact example. Now, when we take a look at motor manufacturer spec sheets, you can essentially take any of your favorite motor manufacturers, open up the spec sheet for one specific size of motor, and see that the electrical power is going to be constant for that series of motor, and you're going to have varying amounts of voltage and current based on the kV selection or wind selection of that motor. What this ultimately tells us is there's no real advantage of power or even torque depending on the kV value that you select. Now, essentially what you do need to know is that motor manufacturers offer you all these different types of winds in order for you to select the best wind to maximize that RPM, the max RPM of that motor based on the voltage that you plan to run. Higher kV does not equal higher power outputs. Now we have to answer this awkward question. But then why do we always hear about this if we're reading through a forum post, a thread post, or a video here on YouTube? Well, let's break it down and look at yet our final example. We take that exact same motor of 2500 kV, we multiply it by a battery we're going to use, a 3S LiPo of a nominal voltage of 11.1 volts, and we're going to get 27,750 RPM. This is the RPM output on that motor. We take the voltage of 11.1, we multiply it by 50 amps, and we're going to get 555 watts of potential power output from our 1200 watt motor. Now, if we do the exact same thing with our 5000 kV motor, we're going to get 11.1 volts multiplied by 5,000, giving us 55,500 RPM. And lastly, 11.1 volts multiplied by our 100 amps gives us that 1,110 watts. This ultimately shows us that the 5000 kV motor is going to give us more power if we operate it at 11.1. If you're going to select that 2500 kV motor and only limit it to 11.1 volts, you're essentially not using the full potential, the full maximum RPM of that motor. So of course you're not going to get the full potential power output of it, you're going to restrict yourself in terms of RPM. And since we know RPM multiplied by torque is going to be power, we know that power is going to be lower than our 5,000 kV example. Now, how about torque? Well, we already proved that the torque is essentially the same. We already put the 50 amps and the 100 amps into our calculation. Therefore, if you use the 50 amps and the 100 amps, we're going to get only 0.19 Newton meters of torque being able to be applied from each one of these motors. If torque is the same, but RPM is significantly lower, overall horsepower or power output of our lower kV motor is going to be less because we're not utilizing its full potential. Now, the only way that we could actually utilize the full potential of this motor is doing what motor manufacturers want us to do, giving us all these different types of kV options. Bump up to the 22.2 volt battery pack. This is a 6-cell, and then you can multiply it by the 50 amps to get that same 1,110 watt of power output. Same as the example here for our 5,000 kV motor. Essentially, our conclusion is kV does not tell us the power potential of a motor. We don't know if the motor is going to be any type of power level based on kV alone. It's simply not enough information. However, if we're working within the same class of motor and we're going to limit the amount of voltage that we apply to a lower kV motor, of course we're not going to get the same power output. We're restricting the potential of that motor. It's like me saying to you and your friend, you can both race down the road as fast as possible, but you're going to only use a stride of about this big. So you're going to have to go like this all the way down while your friend can do whatever he wants to get to maximum speed. You're going to be limited and your power potential is going to be significantly reduced and you're not going to win that race. That's a promise. Same thing here when you relate this to power and kV. That pretty well does it for this video. As always, like the video if you do. Don't forget to hit that sub button so that I can see you guys in that next video. Thanks a lot for watching. See you in the next one.